Okay, that was John Lennon, and imagine, in that last line, sort of imagine a day when the world is one, and man, are we divided. Something to reflect on. John Lennon, one of those performances that is any song I think you could tie together with John Lennon, that is the one. We're doing Math 10, the Intro to Mathematics. One of the things, since this is being broadcast, I sometimes fail to point out, we're coming from Modesto Junior College. We're looking at some reviews. Interesting, if you saw Modesto B yesterday. Nope, it was yesterday's Wall Street Journal. Get the right paper. The Wall Street Journal had an article on a new report on mathematics, and basically turning over a recommendation made in 1989, which said we should probably be using calculators and not focusing on memorizing things like multiplication facts, division facts, and so on. And so we ended up, for about 15 years, with people doing a lot of work in the calculator and not memorizing what we call arithmetic facts. And the report out yesterday basically backed off from the 89 position and said we need to go back to knowing the multiplication tables, the division facts, the addition subtraction facts. They're important, you need to do them, and we need to come back to basics, is the way it's stated. And they're citing Singapore. And in Asia, one of the things that some of the countries had tried doing was taking the same attitude towards arithmetic that we were doing in the United States. Use the calculator, you don't need to know that stuff. And they found that they weren't doing well in international competition. So the Singapore curriculum, as it's now called, returned to a focus on mental arithmetic, and they just drilled on it. And guess what? They do a lot better on international competitions. And it's something that is now being brought back as a recommendation. How long will it take for our schools to change? Probably 5 years would be my guess, before books get redone with the idea of focusing on the idea of using basic skills. It's what I've been arguing forever here at Modesto, at the community college, because I've seen the impact on programs where students have to grab a calculator, do some very basic multiplications and divisions, and it really hurts. And so I've been asking for us as a group to pretty much not use calculators. I don't use them in the algebra sequence, and the only time I really allow a calculator used in the courses I'm teaching right now is in the STAT curriculum, and we tend to use a computer there for the statistical analysis. So anyway, it's interesting to see that the report coming out yesterday in the Wall Street Journal brings us back to where I've been for some time. And that's what our focus is, learning some of those skills, some of those ideas. Now, the work on fractions that we have been doing, I'm going to review. I've left some things on the board that I developed in the last hour. I'd like to look at those and use that as a building block for what we need to do. So Debbie, behind me, I have the idea that we talked about yesterday. This is pretty much, in essence, what it was all about yesterday. We want to add common fractions. Now, certainly, we want more than just common fractions. We want mixed numbers. We're going to look at that today. But just to add common fractions, I need what? The same denominator, a common denominator. And since I had a 5 here and a 5 here, this was my solution. Now, a comment here. I called this a kind of pre-algebra notation, writing things horizontally rather than vertically. This was an intermediate step that I was asking you to use because I feel it prepares you for the pre-algebra and algebra kinds of problems that you're going to do. Now, this brought up the question of this 7 over 5. That was an improper fraction, and we said yesterday you have a choice. You can leave it as 7 over 5, or you can do what? Rewrite it as a mixed number. Now, you have a choice, and certainly for me in this class, either one's acceptable. Now, the criterion you use to make a decision whether or not to do this would probably be in 2 parts. One, if you are doing any kind of multiple choice test where both these answers are given, the writer of the test most likely will consider this preferred. So if you're doing some kind of multiple choice test and you're doing it for a job or something, take this one, even though this is acceptable. Yes?
Is that easier for them to understand it in the rewritten way?
Well, the question I'm being asked, is it easier for the person doing that test, the writer of the test, to do this rather than this? I don't think it has to do with easiness. I think it is a matter that most people just believe what they were told. And most teachers at an elementary school would tell the student, this is a better form. Now, when you get to some of the work we do with multiplying, you have to take this back to here. And so it isn't necessary that you always write this, but it is believed that that's the better form. So there's a kind of culture that says mixed numbers are better than improper fractions. Whether it is true or not, it's the popular wisdom, therefore would be the preferred answer. And I can hear somebody arguing with me in that and saying, well, it's just not popular wisdom, it is right. Okay, so be it. But I like this, and I'll try to show why as we look at other problems that would be, for me, just as acceptable. Now the question, of course, is what happens if the denominators are not the same? And we talked yesterday about multiples, right? We talked about multiples of the denominators. We talked about the LCM. So I'm going to look at this problem. It's 4/5 and 2/3. Now the 4/5 and 2/3, the 5 and 3, what did I have a name for that yesterday? I said they were what? The only thing that can divide both of them is a 1. What did we say was true about 5 and 3? We had a name for it. Something about prime. What kind of prime? Close? Relatively prime. Very good. Relatively prime. They only have one number in common, and that's a 1. Now, if I had 5 and 10, they're not relatively prime. So, if they're relatively prime, what can I do for the common denominator right out of the gate? Multiply them together. And I don't have to make lists. So in this case, we know it's 15. Now, going from 4/5 to 12/15 this way isn't so easy to see, but the process was take 5 into 15, and it goes 3, and then I take that 3 and multiply it by what? The 4. So I've tried to show this in the vertical format. Now this vertical format is more in keeping with what we do in arithmetic rather than algebra. So I say I want 4/5 as something over 15. So typically you would see it this way. So you'd say 4/5 is something over 15, and then you'd say, what do I have to multiply times 5 to get 15? And your answer is 3. What I do here, I must do what? Up here also. And what do we call that property with what I'm doing there? We have a name for it. I have the letters here. What do the BPF stand for? It's not British Petroleum. BPF. Basic principle of fraction. I suppose you want more points for that too. Uh-huh. The master of acquiring points. BPF, the basic principle of fractions. And it says whatever I do to the denominator, I must do to the numerator. And what are my two choices? I can either multiply or divide or multiply, your choice. So I multiplied here by 3, so I must do the same thing to the top number by 3, and that gave me the 12. Same game down here. Technically, you wouldn't know the 10 yet, so you'd say what? 3 goes into 15 5 times, or you can ask what's the missing factor. If I have 3, what can I multiply by that 3 to get what? The 15. And your answer is 5. Since I multiplied here by 5, I must multiply the numerator by 5. That gave me the 10. Agreed? Now that gives you 22 over the 15 again, and so we get our same answer at the bottom, so that doesn't change in the process. Are we okay there? Yes. Any questions? Now if you didn't remember that since the 3 and the 5 are relatively prime, you could have said what? 3, 6, 9, 12, 15. Then you could count by 5s. 5, 10, 15. And the 15's what? Your smallest number in both lists. So that is a common multiple. These are the multiples of 3, multiples of 5, and you can get your LCM that way, or your LCD. Least common, and if it's the denominator, you say LCD. If it were just multiples, it would be LCM. Any question there? Now, the thing I tried to mention about what I did here, that this form, okay, is a very important process in algebra, and the illustration I gave for that intermediate step, you can see on the upper right corner of the television monitor. So Debbie, I want to have that left justified to here basically at some point, and then I'll go into that. So I'm going to just move over to the other. There we go. Thank you. I have a over 3 and b over 3, and if these are the same denominator, I can just write this, correct? A plus b over 3. So the question I asked the last go-around of this, let me simply erase what I had. This was the original question. If I have a over 3 and b over 5, I can't do what I did here because their denominators are different, correct? So what I wanted to do is look at these two numbers, these two expressions. I'll be more careful there because I'm talking about two expressions. A over 3 is an expression, b over 5 is an expression, and I want to add them. They need a common denominator, and the common denominator is still what? 15, just like it was before. So I play the same game. What can I multiply by 3 to get 15? The 5. Agreed? Now, I'm reluctant to use that x for multiplication, and I'm looking at that screen, and it looks nearly too small, so I'll write it larger, but we get 3 times 5, and that's how we got our 15. Then I should do what? Same thing up here, and that's the basic principle of fractions. Now, one little small addendum here. You waving or just the fly? Oh, okay. The fly's learning algebra, learning pre-algebra, and arithmetic simultaneously. About geography, too, and who to avoid. Okay, with all that, I don't usually use the x for multiplication because we tend to use x just like we use a and b. So rather than doing that, I'm going to use a big dot for a moment, and it's not a decimal point. It's sort of in the middle, and that means multiply. So a times 5 is 5a. Over what? 15. Okay, 5 goes into 15. 3 times, right? 5 goes into 15, 3. So I'll put the big dot and a 3 and a big dot and a 3. So that's 3b. So now that intermediate step, and I'll just rotate, there's my 5a plus my 3b over what?
15.
The common 15. Now that's an algebra problem. You'll do that kind of problem in pre-algebra, in algebra. It's the kind of thing we've done in the intermediate algebra course. That would be simplifying your answer, and that's all you can do. You stop at that point. Now, if you want to know what that represents, somebody has to tell you what A is, and somebody has to tell you what B is. And I may have different values of A and B, and I get a new number each time I have a new value of A and B. Now, that's why I like this intermediate step that we talked about. So the intermediate step is where you show the numerator, and then you put it over the common denominator. Now, again, I'll remind you, one of the things that if you don't do fractions very much, keeping in mind the numerator and the denominator, we've talked about this one prime before, I think, but if I haven't, I'll do it now. If you're trying to remember which one's on top and which one's on the bottom, just remember this. makes it a little bit racy for the lecture this morning. But nude. NU, numerator, DE, denominator. So if you write that out, it tells you which one's the top, which one's the bottom. Okay? Now, Debbie, I'm going to want to change the problem so it's much more demanding. So if you'll bring camera 2 over to, well, first I assume you have to go to 1 first. Thank you. And then bring 2 over to the side. And what I'm going to need, maybe, let's see what we can do. With what I have here on the board, because I'm going to walk off this camera shot here. Let me see what we have. Okay, this is good. Maybe keep in mind what we had up here at the top. There we go. And just slide it over just as we pick up this answer here, and I'd like to leave that on the screen, nude and all. Okay, there we go. I'll leave that on the screen, and I'm going to come over here to the sideboard now and show you a pretty miserable looking problem. And the comment here as I do this, if you count by 3s and count by 5s, it's not bad. This one really is a bear. Now, you see 11 over 48, 13 over 56, they won't reduce, and you see a 336 there. I don't think that 336 you're going to pull out of the air. I mean, if you can, you're doing good. I can't do that. So the 336, question, where would we get that? Well, I could do this. I could count by 48s. 48, 96, 144. Count by 56, 112, 168. Keep trucking. Do you realize 300 is going to be down here a ways? Quite a ways? And it's going to be tough getting there? So the question, how can I do that? And I'm going to go ahead and erase what I did here for a moment and redo that. I'm going to do prime factoring. Now this is looking ahead a little bit, but I'm going on the basis it's better to see this 2 or 3 times than just once. So I'm going to list the primes. My primes are 2, 3, 5, 7, 11, 13, 17, 19. Can you rattle those off in the morning before coffee? If you can't, practice. Every morning before you get to drink that first sip of orange juice, that first sip of coffee, see if you can rattle off those primes. You only have to go to 19. They go forever, so you could forever never have coffee. That would be not good. Okay, I'm going to start with my 48, and then what do I start dividing by? The 2, agreed? So 2 into 48, 24. Then do the 2 again. I hope this is starting to get boring. I really hope it is, because if it is, you've got it. Okay? We okay in that? So let's write this with exponents. So 48 can be written as how? Excellent. I count the number of 2's, and I have 1, 2, 3, 4. So 2 to the 4th and 3 to the 1st, with a dot in between for the moment. Do we agree? I'm seeing a few head bobs like this, and that tells me you agree. I've seen 3 head bobs. That does not make a full agreement, but I'm optimistic. What are we going to do with the 56? Same thing. So 56, here we go. 2. What do I get? Do the division in your head if you can. 28. Does that seem comfortable? Short divisions in your head? If that's not coming quickly for you, then practice, practice, practice. We need a training camp. 14. Okay. 14. That went faster.
7.
And then the 7.
1. Oh, no, you're right.
Okay. You were ahead of me. I'm going to write the 7 here. Thank you for keeping me honest. Now what? 56 is? I have the 2 written 1, 2, 3 times. So 2 to the 3rd. 7 to the 1st. Isn't that getting old? You can do this much easier than you were before. If you can't, do more of it. until this is something that's nearly automatic.
Are you going to prefer the dot over the X
No, the question is, am I going to prefer the dot over the X? The X is fine. I'm just wanting to emphasize today that the dot means multiplication also. And I shouldn't probably confuse you with the dot, but since I have it there, I'm not going to go back and replace it with an X. Now, instead of putting X's after your name on the letter you write, you put dot, dot, dot. You just didn't get that. Okay. I want the LCM, the LCD. Here's the easy part. We did all the hard work. Now what you do is you write down the primes that you used in the division. You only write them once. So what primes did I divide by? 2s, 3s, and 7s, right? Those are the only primes I had. So you write them down. 2, 3, and 7. Now I'm going to look for exponents. What's the highest exponent that you had on the 2? You had a 2 to the 4th, and you had a what? 2 to the 3rd. What was the highest? So I write down the highest. That's all. So on 3, the highest exponent was a 1. The highest exponent in a 7 was a 1. So my question, what is 2 times 2 times 2 times 2 times 3 times 7? That is my LCD. So let's try it. 3 times 7? 21, agreed? Now 2 to the 4th. Now 2 to the 4th is not 8. You're thinking of adding. 32 is too big. 16 is just right. Okay? Have to take some points off. Now 16 times 21. Okay, I'm keeping track. Now 1 times 16 is 16. 2 times 16, 32. 3, 3, 6. That is where I got my 336 from. Let's slide over. Okay, there's my 336. Now the question. Here's the question of the day. How can I get the numerator? What do I have to do? Divide 48 into 336. I could. I don't want to. That's too much work. So let me show you the shortcut. Now this is why I'm doing this today and probably tomorrow. And I can't do it tomorrow because what's tomorrow? Vitamin C time, oranges, the orange book, the counting unit. So it'll be Monday, but I'm going to show you the shortcut now, and let's see if you remember it next Monday. Let's slide back now, Debbie. Okay, that's good. Here's the LCD, and here's what I had, correct? So there's my 48. Here's what I want it to look like. How are these different? This is Sesame Street time. How are these different? This and this differ from that 7, correct? So if I multiplied this times 7, they'd look alike. Huh? Okay, slide back. Debbie's going to get a lot of panning exercise. We could call that going for gold. Okay, so 7 times 48, I know that. And notice I did resort back to the times. Now what's 7 times 11? 77. Okay, back we go. Okay, here's what I want. Here is what I have. What's missing this time? Not only the 3, a single 2, correct? I have 3 2's here, 4 2's here. I need another 2 and a 3. What's 2 times 3? 6. Do you see where I'm getting that 6? I compare these two. Sesame Street criterion, what is different? This one has a 3, this doesn't, so I need a 3. This has 2 times 2 times 2, that's 3 2's. This has 4 of them multiplied together, so I'm missing a 2. A 3 and a 2 give me a 6. Okay, pan time. So I'm going to multiply this by 6, and what do I get in the numerator? Now see, this is where I really get concerned. Okay, that 78 should have popped into your head about 4 seconds before it did. Because 6 times 3 is 18, carry a 1, that gives you a 7, so that's 78. That should be a little red flag going off in your head, meaning I've got to do these faster. Okay, intermediate step, what is it going to be? Intermediate step time. Okay, camera 1, back to, will you focus on the 4 over 5 plus 2 over 3, left third of the board, more or less.
77 plus.
Okay, that's the intermediate step where I want to take the 12 and 10 and add them together before I put it over the 15. So, what did I hear? 77 plus 78 over 336, intermediate step. Okay, we're having fun. In your head, 70 and 70 would be 140, right? 70 and 70 would be 140. 7 and 8 would be 15. 140 and 15, 155. Do you see how I did the addition there? I said I have 70 plus 70 is 140, and then the 7 and 8, another 15, hence 155. Now the question, is this reduced? Give me an argument. What are the only numbers I need to worry about to see if this is reduced? Okay, you're saying the last two numbers. Nah, I won't buy that. The 5 and 6 tell me a story. The 5 in the first, the numerator, means it can be divided by 5. The 6 in the denominator means it can be divided by 2 or 3, therefore, or 6, and so on. What do I need to worry about? Okay, Debbie, we're going to slide. Yes, but which ones do I have to worry about? When I got my LCD, the only thing that involved was a 2, a 3, and a 7, correct? So if I'm going to slide back over now and look at this number, the only way that I could reduce both of these, divide both, is a 2, 3, or 7. Will a 2 go into 155? No. Will 3 go into 155? Give me the argument. Has to add up to a multiple of 3. 5 and 5 is 10. 1 more makes 11. 3 will not go into 11. So 3's out. So what's the only number I have to worry about? The 7. Will 7 go into 155 evenly? Okay, we try that. 155 divided by 7. It goes at 2 with 1 left over. That'll go at 2, but still what? 1 left over, not evenly. So 7 didn't work. That's reduced. I'm done. Now, if you're comfortable with prime factoring, and you can do that, you can do every addition problem we ever give you. Any questions?
Basically falls back to prime factoring.
Oh, yes, everything. The question was, does everything fall back to prime factoring, basically? And the answer is yes. An enthusiastic yes. Primes rule. Primes are important. We can reduce fractions with primes, we can find LCDs with primes, and we can decide whether or not this is reduced with the primes. We call this prime time. Prime time presentations, even though it's not at the evening hour. Okay. Now, let's see what we have. We're going to slide over, Debbie, because I don't have an idea in the world what's behind me, so we'll just slide over and see where we go. Ah, right there. Okay. Now, this is a little different kind of problem because we have mixed numbers. Now, with mixed numbers, we have to be careful. Now, no, not that far yet. Stay back a little bit more. Keep tweaking. There we go. At least for the people watching on television, they don't know what else is there, and that's good until we get there. Now, this problem that I have, you can see that I have 1 1/3, 2 1/4, and what we typically do is change the 1/3 to 4/12, the 1/4 to 3/12. So my first question, how did I get the 12? Why is it the least common denominator? Why was I able to multiply? Give me the rationale. Okay, it's 3 times 4, but what's critical about the 3 and 4? They are what? 3 and 4 are, fill in the blank. Relatively prime. If they're relatively prime, I can take their product means multiply. Hence, 12 is my answer. And of course, I'm sure that if you sat there and said 3, 6, 9, 12, 4, 8, 12, you'd say, yes, I agree. 12 is the LCM, therefore the LCD, and we just saved ourselves some time. Now let me show you what happens sometimes here that's frustrating. That's sometimes what I see in the answer. Somebody was so excited after they did all this work with the fractions and they got the 7/12, they said, I'm done. Instead of what? Add the 2 and the 1 together. So I sometimes recommend do this part first, then go to your fractions and you won't get trapped. Now one of the questions that was asked at the last hour, and I'm just going to get out of the way this far, and by the way, you can see as I move a little bit further, 3 and 7/12 can be written as what? 43/12. So if you're looking at the screen, again, 12 times 3 is 36. So add 7 and you get 43. So if I look here and I say I have this 12, multiply it by the 3, 36, add 7, I get the 43/12. But notice what I've done here is I've taken the 4/3. Notice how I changed from 1 1/3 to 4/3. We did that in the review test. Then I took what? The 2 1/4 and multiplied. 4 times 2 is 8, and 1 is the 9/4. Then what? I just changed those to new fractions. 27 and 16 is 43. Now just a comment. That's a way of getting around having mixed numbers. Would you expect that as to be something that's to an advantage right now for adding? What's your reaction? You have a choice. You can do it this way or this way. We get the same basic answer. Is there any advantage that you're seeing to this over here?
Yes.
Okay, what's your advantage?
We don't have to do as much.
Okay, see, maybe it's a little less math. My guess is some people might argue with you that 27 is a bigger number, therefore it's more math than is a 3. Okay, so I think there's an argument either way in that. This is a way of avoiding mixed numbers and changing them to improper fractions. If I do a subtraction problem, as we do on Monday, because tomorrow again is going to be on the counting unit. But on Monday we're going to look at subtraction, and this will be a technique that will get us out of trouble. So it is something that you may want to reflect on as a good thing. Right now it's probably not so good, but it'll be a good thing later. Okay, let's slide further, Debbie. This is a surprise to me, what I'm seeing. Okay. In this problem, what I have is 1 2/3, 2 3/4. Now, I've shown you what's happened here in the process. In this process, the 2/3 I'm writing as 12. 4 times 2 is 8. Do you see the 8/12? And I had 3/4, so the 4 into 12 is 3. Can you pull it a little bit tighter, just this top part here, Debbie, for me? Because I'm having trouble seeing those numbers, and I suspect people at home are. So 4 into 12 goes 3. 3 times 3 is 9. 3 into 12 goes 4, and 4 times 2 is 8. So we play this game. 8 and 9 is what? 17. Over the 12, the 2 and the 1 is 3, and you stop and say, life is good. You get your paper back, and you see this, -5. a mixed number must have an improper fraction here, not, didn't say that well. Back up, rewind, try one more time. A mixed number must have a proper fraction here, not an improper. So this is bad form. Do you understand 17 over 12 is 1 and 5/12? Again, 17 over 12 is 1 and 5/12. So this is what we really mean is now we come down just a little bit more there. So the 3 and 17 over 12 is really 3 plus 1 and 5/12. And that gives you 4 and 5/12. This will be the trap that you'll get in homework if you aren't careful. Is there any question in that part? Okay, I'm just going to, maybe Debbie, as I walk off camera, can you try to get from here down to here and just pretty much there, and I'll walk off camera because I'd like to look at the kind of problems that we're doing in this set before I talk about that last problem I have up there. So just look at that carefully and let's see if you have any questions. Are we comfortable with that? If not, let me know so I can respond. So we're comfortable there. Which part? Okay.
Well, from 3 plus 17 or 12,
Okay, so that last part is a little bit of confusion. So we're talking about right here. Now, do you agree that 17 over 12 is 1 and 5/12?
Yeah, 12 goes into 17, 120.
Adrian, do we agree? Okay, now your 3 plus 1 is just your 4 and 5/12. And now this is in the form of what? A whole number and a proper fraction. So that's good form. This is not good form because I had an improper fraction here. So the one at the bottom is the preferred form.
So you just never lose the 3. You just add it to the...
I'm adding the 3 and the 1 that came from the 17 over 12. We okay? That's a crucial step here because you will be inclined to just stop here. But if that's not proper, you've got to rewrite it. And I guess the key is this. What does a rephrase that. What does a mixed number mean when I say 3 and 17/12? It means you have 3 plus what? 17 over 12. 1 and a third means 1 plus a third. So that means I'm adding 17/12 to 3. But 17 over 12 is 1 and 5/12, which means 1 plus 5/12. So the 3 and 1 give you 4 and your 5/12. Now how could you avoid all that? What could you do? Back to improper fractions. Okay, so let me carry that through. And I'll just erase what I have up there because there's a point here that's still causing some frustration. Let's see. Let's try it. I have 1 2/3. And maybe this will help get you around a problem if you're having difficulty there. Improper fractions, please. 1 2/3. What is the improper fraction?
16 over 12 or 8/12?
No, I just want this much. Something over 3.
Oh, 5.
5 over 3, agreed? 3 times 1 plus 2. So 5 over 3, are we in agreement? That threw you for a moment, it seems. Now what? 11 over 4. 4 times 2 is 8. And you're 3. 11 over 4. But I want them as what now? Common denominator of 12 still. Okay, so the 4 into 12 is 3. So I took 3 times 4, so I have to take 3 times 11. 33. Okay. What up here?
4 times 3.
Okay, I needed a 4 times 3 to get 12. Basic principle of fractions. 4 times 5? 20. Now, intermediate step. And that gives you what?
53. Sorry.
53. Okay, over 12. Okay, divide in your head. 12 into 53. 4 times. That's 48. What's left over?
5.
There's your alternative. Same answer, right? You can see here I had the 3 plus 1 and 5/12, which gave me the 4 and 5/12. So I'll just walk off a little bit there, and Debbie, you can maybe pull out just a little bit. Same answer, right? Now in this technique up here, I didn't have to do what? I didn't have to deal with that 17/12. What's the downside? Bigger numbers. I had 8s and 9s, now I have 20s and 33s. I have a 53, I didn't have anything like that. And big numbers do what? Usually give us some trouble, so you have to be careful. Well, let's see what we have. There are some simple problems that at times I think cause some frustration. We're going to get to that in page 91. I just want to look at that for a moment. I'm at the bottom of the page in 91.
May I ask you a
Okay, let me cut to this just for a moment before I answer the question. Okay, Debbie. Now this is the problem I wanted to reference, then I will answer some questions. 1 1/10 added to 5. There's nothing to be added to the 1/10, correct? So you can just bring it down. And then the 5 and 1 is 6. That's one version of it. Coming off there for a moment, the second one related to that is this one at the top of 92, where I have this problem. Now I have two fractions, but I'm missing what? The whole number part here. So that's like a 0. So you add the 2/3 and 3/4, and then you still have your 1. And I show that solution. So let me come off that for a moment. What we end up getting is this, and there's that 17/12 again. So you have 1 and 17/12, so what do you do to the 17 over 12? Rewrite it as 1 and 5/12. So let me just slide over. And that's exactly the problem we were talking about on the board. That's on page 92. And hopefully that will provide a reference for you. Okay, question.
On the homework last night, there was one problem that had several primes on it. Is that okay with a fraction, or?
Several primes on it.
It was, you had to 450. It was like 120 over 450, and you wanted the prime.
Okay, I wanted you to take a fraction, 120 over 450, and reduce it using primes.
Right.
So I expected you to take the 120 and write it as 2 times 2 times and so on.
So it doesn't matter how many you get. It's okay.
No,
It
you want to
doesn't
write all
stop
the
at
primes
3.
out. You don't want to use exponents there.
Okay.
So if you had 3 2's, you'd write 2 times 2 times 2. If you had 4 2's, you'd write 2 times 2 times 2 times 2.
Okay, so that's
And then
what I was
just
wondering.
look for the prime in the top, the prime in the bottom, and cancel them. Cross them out. Leave ones. It's okay? Now, where is the wrinkle then that you have to be careful of with adding fractions? And Debbie, it's back to that problem we just had on the side board. Let's go back there one more time. That's the wrinkle you have to be careful in doing. So I'd like you to look at page 94 and 95. And just the point, if I look at 94, pretty straightforward, I hope. If you can find these denominators in your head, you don't need to show any work. So 4 and 5 in problem 2 are relatively prime. So what is the LCD for problem 2? The 20, 4 times 5. Again, the 5 and the 4 have only one number that divides into them evenly. That's a 1. That makes them relatively prime. So 4 times 5 is 20 is my LCD. But notice in number 4, the 6 and 4 are not relatively prime because the 6 can be divided by a 2 and a 3. This can be divided by 2 and 1. They're not relatively prime. But you still can see the LCD, and what do you get? Now I hope you see a 12 there. Now, otherwise, you could do what? Take 4, 8, 12, 6, 12, and get there. Coming off that for a moment. On page 95, here's just a couple of problems that are very typical. Notice I've done them vertically to make it easier for you. Be careful on number 12 and 11. I think in both cases you're going to end up with improper fractions when you add, and then you have to make sure that you have your mixed number in the form it should be. Now, as I come off there for a moment, Debbie, and come down, be careful in number 13 and 14, because this is the kind of thing we were just talking about in an earlier page. There's nothing to be added to the 7 over 10, so it doesn't mess things up. There's nothing to be added to the 7, and so that doesn't mess things up. Those should be fairly straightforward. Now, let's go back to the review test. And I believe that's about 191, somewhere in there. Nope, further than that. 199. Just under 200. So 199. Let's look at these first two problems. Pretty straightforward, right? Denominator's the same. I'd like to see an intermediate step and make sure you reduce your fractions. So I want to see intermediate steps and reduce your fractions. Coming off there, as we come down to something like numbers 3 and 4, what's different about these? The denominators are not the same. So if you can eyeball the denominator, you don't need to show any work as to how you got that denominator. Coming off that, I'm going to come down to this problem. Now this one, be careful. That's where the trap is. You're going to get an improper fraction that you have to do something about. Then finally, there's this problem, which may throw you a little bit because suddenly I'm throwing 3 numbers at you. An LCM. I want to see your work, and I want you to give me the multiples of 4, the multiples of 6, and the multiples of 3. This would be like having 3 fractions, different denominators, and you have to find an LCD. There's a practical solution, should I say maybe a practical problem related to that finding an LCM of 3 numbers. Let me give you an illustration with the buses. Bus routes come back to the transfer station, right? Sometimes it takes an hour, sometimes 30 minutes, and so on. So let's say you have 3 bus routes, and they all leave at 8 o'clock in the morning, same time. One has a 10-minute circuit, very quick. It's downtown, just hits a few blocks. Another one has a 20-minute circuit before it comes back, another 30 minutes. When's the smallest amount of time before they're all back at the same spot, that bus transfer station? Well, you have 10, 20, and 30. What are the multiples of 10? 10, 20, 30, 40, 50, 60. Multiples of 20. 20, 40, 60. Multiples of 30. 30, 60. The smallest number in all 3 lists? 60. So in 60 minutes, those 3 buses will again be at the station at the same time. So if you left something on the first bus, and you can't remember which bus it was, you know they're all back in an hour, so you sit there waiting for an hour and then check all 3 buses. Homework, review test number 9 is going to be due. We're at the end of the presentation in terms of when I need to clear the television broadcast. So we started with John Lennon with Imagine, and did you want to go with that, or did you have a choice as you?
No, I chose Don't Let Me Down.
Oh, thank you.